Welcome back to the deep dive. Today we are moving past theory and getting right into the architecture of resilience.
That's right.
If you're a DevOps or an SRE professional who's already sort of mastered the basics, you know what horizontal scaling is, you can spin up a VM. This is for you.
Yes.
We're talking about the real-world headaches, managing explosive traffic spikes, optimizing costs when the load drops, and making sure your deployments never, ever impact the customer.
That's the mission today. Absolutely. We're moving from knowing what these tools are to mastering the how and the why.
The actual implementation.
We've gone through a huge stack of source material, all focused on those intermediate to expert level challenges. Things like compute engine capacity, the two-layered scaling of DKE, and maybe most critically, how you preempt failure before it even hits your users.
Okay, let's unpack this then. The sources we have give some really clear direction on those critical architectural decisions.
The kind that really separate a competent admin from a true architect.
Exactly. Someone who can build resilient, cost-optimized systems. So we need to explore the non-intuitive solutions, their required safety nets, and the data-driven optimization tools.
Sounds good.
So we're diving straight into Section 1, the art of intelligent scaling and resource allocation. And we have to start with the oldest debate in the book, when to scale out and when to scale up.
Indeed. It's the fundamental decision everyone faces. Horizontal versus vertical.
Right. Do you add more sort of commodity machines, or do you just make your existing one a monster?
Well, the definition is simple. The implementation, especially when you factor in reliability, is, well, it's nuanced.
So let's start with the classic scenario. When you see an overloaded system, the first instinct is usually horizontal, isn't it?
Almost always.
The sources detail is perfect example. An overloaded, high-request, stateless API. It's on a single compute engine instance, and it's just constantly timing out.
And you check the instance. The root cause is, textbook. High volume of concurrent requests, and the single instance just runs out of memory.
It's hit a wall.
A hard physical resource ceiling. And look, you could throw more RAM at it, scale vertically, and maybe that buys you a week.
But it's a Band-Aid.
It's a Band-Aid. It doesn't solve the two fundamental architectural flaws. You have no distribution, and you have a single point of failure.
So the recommended fix is the simplest horizontal solution. But we really have to emphasize the reliability component here. It's not just about adding more instances.
Precisely. The core fix is confirmed. You have to set up additional service instances across different zones and then use a load balancer to distribute the traffic between all of them.
And the key phrase there is different zones. Why is that so critical?
Because that immediately gives you geographical redundancy. Let's say your original VM was in US Central 1A.
Oh, yeah?
If that whole zone has an outage, your entire service is down, hard down.
Right.
But by distributing across US Central 1B and US Central 1C, that outage in Zone A just becomes, a momentary dip in your total capacity. It's not a catastrophic failure.
That distribution across failure domains is it's absolutely crucial. And it ties directly back to your SLOs, your service level objectives.
A single instance deployment can't, by definition, meet a high availability SLO. It's just not possible.
But what about reliability, even when you only think you need one instance? We saw a scenario where a production service runs on a single compute engine instance.
And when it fails, maybe a memory leak or an app crash.
Someone has to manually intervene. They have to get an alert, log in, delete the crashing instance, and then create a new one from scratch.
That process is the definition of toil in modern SRE terms. It is unacceptable.
It's reactive, it's slow, and you're burning human time on a completely predictable mechanical failure.
The SRE principle here demands automation. It demands self-healing. And the solution is actually pretty simple, but it's transformative.
So what's the standard baseline reliability fix for compute engine?
You create a managed instance group, a MIG, with a target size of a single instance, and you use health checks to determine the system's status.
So you're turning that one static resource into a managed fleet of one.
Exactly. And the key mechanism is that health check. It's not just pinging the VM.
No.
It's checking a specific endpoint on your application. It's checking if the application is healthy.
So if that health check fails for any reason...
The MIG doesn't wait for a human. It assumes its desired state of one healthy instance has been violated.
And it acts.
It automatically terminates that unhealthy instance and provisions a new, clean one from the template. This just drastically improves your availability SLI.
You're moving the responsibility for failure detection and recovery from A tired human operator at 3 a.m. to the underlying cloud infrastructure.
That's it. It's the horizontal reliability philosophy, but applied even to a single machine deployment. It's a fundamental building block.
That makes perfect sense for self-healing.
Yeah.
But what if we do need to scale vertically? There are some really surprising reasons why you'd do that.
Yes. This is where we pivot to vertical scaling and hit a nugget of knowledge that absolutely blindsides intermediate engineers.
The network performance bottleneck.
Exactly. People assume, my CPU is running at 10%, I've got plenty of room to grow, but that's not always true if your workload is data intensive.
I remember this case so clearly from the sources. You've got a service using a standard entry-level VM, like an N2 standard 2.
Right, 2 vCPUs.
And it's serving large files, maybe video assets or software updates, and users are reporting painfully slow downloads.
But the team checks the monitoring dashboards, and the CPU and memory are just coasting, maybe 15% utilization.
So where's the bottleneck? It's not the CPU.
The bottleneck is hidden in the networking metrics. The dashboard shows the VMs are running at peak network throughput.
So the instance is saturated.
It's saturated, but not computationally. It's saturated in terms of the maximum rate it is allowed to push data out.
So it's an artificial cap?
It's a restriction imposed by the hypervisor, and it's tied directly to the size of the virtual hardware. You can't just request more network capacity independently of the machine size.
You are capped.
You are. So the non-intuitive fix is a vertical scaling one. You have to change the machine type for your VMs to a significantly larger tier, for instance, upgrading from N2 standard 2 to N2 standard 8.
So you go from 2 vCPUs to 8 vCPUs.
Right.
Now, I have to challenge this because this is where the cost optimization devil comes in. We've just jumped from a machine that costs, say, $50 a month to one that costs $200 a month.
A 4x increase.
Purely to get faster downloads, even though our CPU usage is still only at 10%. I mean, isn't that just grossly inefficient?
It is absolutely less efficient in terms of your compute to cost ratio, but it's crucial for meeting a performance SLO, which in this case is user download speed.
Okay, so explain the why. Why is it engineered this way?
It's rooted in the platform's economics and engineering. Cloud platforms tied network throughput directly to the CPU size for a few reasons: guarantees, resource allocation, and preventing the noisy neighbor problem.
Right. You don't want a tiny VM hogging the whole physical network card.
Exactly. If you gave a small VM massive network throughput, it could consume shared resources disproportionately and impact other customers on the same physical host.
So the larger machine type is essentially a resource reservation token. By paying for the bigger CPU, even if you don't use all the cycles, you are guaranteeing yourself a higher network bandwidth ceiling.
That is the key takeaway. You're paying for a commensurate slice of the physical network fabric. Vertical scaling isn't just about adding RAM or cores for calculation.
It's about unlocking these hidden resource gates.
Yes. If you are serving large files, streaming video, or dealing with high volumes of replication traffic, you have to be right-sizing based on your network throughput requirements, not just your CPU utilization.
That's a subtle but really critical realization for moving past that beginner-level resource management.
It is.
Okay, so we've established that single VM scaling is relatively straightforward. You size up or you multiply with the MIG. But moving on to containerized environments like GKE,
The complexity multiplies.
it multiplies by 2 because you have 2 distinct layers interacting. The application processes, which are the pods, and then the underlying virtual infrastructure, the nodes.
And getting this interaction right is the very definition of cloud elasticity. This is what we're aiming for.
Full optimization.
Running only the resources we need, precisely when we need them, without ever compromising the user experience.
Let's use that classic e-commerce scenario we reviewed. A large website using JVM microservices running in GKE. The load is highly cyclical.
Massive influx during business hours, dropping to near zero overnight.
And the legacy approach before you have proper automation was to provision enough nodes and pods to handle the 4 p.m. spike.
Which means you have huge idle costs at 4 a.m.
That overhead just destroys your cost efficiency.
It does. The only way to optimize resource usage and ensure consistent performance is to implement this 2-layered scaling strategy at the same time. You have to configure the horizontal pod autoscaler, HPA, and simultaneously, you have to enable the cluster autoscaler.
Okay, let's dedicate some time to really breaking down this dance, because I think intermediate engineers often misunderstand the order of operations here.
And their respective roles.
So the HPA, that's the application traffic cop.
Right. The HPA is monitoring resource metrics. Most commonly, it's average CPU utilization across a deployment.
But ideally something better.
Ideally custom metrics like requests per second or queue depth, and based on a target, say 70% CPU, it automatically increases or decreases the number of pod replicas.
So in that e-commerce scenario, as traffic hits, the HPA sees the CPU climb and it scales the app layer. It adds more pods.
Exactly.
Now let's assume traffic spikes really rapidly. The HPA correctly sees 90% utilization and decides to launch, say, 10 new pods immediately.
Okay.
But the existing nodes in the GKE cluster might only have capacity for 2 of those new pods, so the remaining 8 pods instantly become pending.
Or worse, unschedulable.
Right, and the Kubernetes scheduler has nowhere to place them, so the scaling action just stops dead.
And this is precisely where the cluster autoscaler comes in. It is not looking at CPU utilization within a pod.
It's looking at the bigger picture.
It's looking at the cluster's health, and it's specifically monitoring for those unschedulable pods. When it sees those 8 pending pods, it recognizes a capacity shortage.
And it springs into action.
It automatically requests the provisioning of new compute engine VMs to join the GKE cluster as nodes. It scales the infrastructure.
So the HPA creates the demand, and the cluster autoscaler satisfies the supply. It's a beautiful partnership.
It is.
But there's a critical configuration detail here to prevent cost blowouts and unstable scaling. I'm talking about the stabilization periods.
Oh, absolutely. Scaling up should be fast. Scaling down must be slow and deliberate.
Why is that?
Well, if the HPA scales down too quickly right after a momentary spike, and then traffic immediately returns, you get what's called thrashing.
The cluster is just constantly scaling up and down,
wasting resources and time. To prevent this, you tune the scale-down delay parameter. This ensures that after the spike subsides, the HPA waits for a defined period, maybe 5 to 15 minutes, before it reduces the number of pods.
It makes sure the dip is real and not just a blip.
Exactly. It guarantees the cluster doesn't react prematurely.
And on the infrastructure side, the cluster autoscaler has its own safety settings too, doesn't it? It has to safely drain the nodes it wants to terminate.
Correct. You can't just yank the rug out from under live application pods.
That would be bad.
When the cluster autoscaler decides to scale down at night, it needs to ensure that all the active pods on the node it wants to terminate are gracefully moved to other nodes before it issues the delete VM command.
So it preserves data integrity and continuity.
Right. The collaboration between the two, tuning both the HPA stabilization windows and the cluster autoscaler drain periods, that's what achieves true cost-optimized elasticity.
It's so clear. If you only enable HPA, you hit capacity ceilings.
And if you only enable the cluster autoscaler, you're just paying for idle nodes unnecessarily.
We can see this principle applied perfectly in that pub/sub transaction example from the sources.
Yes.
You have a microservice processing orders from a queue during a major sales event. The spike causes the queue backlog to grow really rapidly.
Which leads to SOC inaccuracies because the application is processing old, stale data.
The core issue is just throughput. The application is pulling messages slower than the system is pushing them.
The instantaneous fix, according to the sources, is simple. Increase the number of pod replicas. This is an immediate HPA action.
Or, even better, the HPO should be configured to recognize the pub/sub queue depth as a custom metric.
Yes, that is far superior to using CPU utilization in this case.
Explain why.
Well, think about it. If the system is at 30% CPU busy but has 10,000 messages waiting in the queue, it needs to scale urgently.
Right.
But if it's at 90% CPU busy but has no messages waiting, it's actually just being efficient. It's not struggling.
So when you're dealing with these asynchronous queue-driven workloads, scaling should be driven by the metric of demand, the queue length, not the metric of current utilization.
Exactly right. This ensures the system proactively scales to empty the queue and prevent those business-critical failures like stock inaccuracies. An HPA based on queue length will fire faster and more appropriately than one waiting for a CPU spike.
Okay, let's elevate the complexity now. Let's get to the advanced stuff.
Let's do it. We're dealing with compute-heavy, varying-size batch processing jobs arriving unpredictably from external third parties.
And the requirement is absolute cost minimization while ensuring rapid processing. We need a system that basically sleeps for days but can wake up instantly when data lands.
This architecture required a secure ingestion, a serverless trigger, and ephemeral extensive compute. It's the highest level of horizontal scaling optimization.
So, starting with that secure ingestion piece, the data is coming from multiple external entities.
So you need a highly available, robust, and secure landing zone. The source material recommends providing a cloud storage bucket for uploads, combined with the appropriate IAM controls.
The bucket gives you durability, and it can handle massive concurrent uploads gracefully.
It can. And the genius is in the trigger mechanism. We don't want a polling service that's constantly running and costing money.
We want zero-cost waiting.
And for that, we implement a cloud function triggered by the google.storage.object.finalize event. This is our serverless glue.
So the cloud function only consumes resources for the few milliseconds it takes to execute its logic. It wakes up precisely when a new, complete object has landed in the bucket.
Right.
And because the processing is heavy, it needs specialized software, large machine types. The function doesn't do the work itself, does it?
No. It acts as the orchestrator. Its role is to call the Compute Engine API and execute the necessary scaling action. It instructs the API to scale up a specific Compute Engine auto-scaling managed instance group that is preloaded with the processing software.
And it could even be smart about it, right? It could inspect the file size from the event payload to calculate how big the MIG needs to be.
Absolutely. And crucially, that instance group is configured with an aggressive auto-scaling policy that ensures the instances terminate themselves when the processing completes and utilization drops to zero.
That's the full life cycle loop. Data lands, a trigger fires, the compute fleet is summoned, processing is done, and the fleet dismisses itself.
The only ongoing costs are the negligible Cloud Function execution fees and the storage fees for the source data. It's an incredibly efficient pattern.
This demonstrates that advanced utilization of horizontal scaling combined with serverless triggers. It's the ideal pattern for high variability, batch-style, ETL, or rendering jobs.
Maximum elasticity, minimal total cost of ownership.
Before I move on to safety, there's a quick but highly specific latency issue in App Engine that requires an expert fix.
Yes, the post-spike latency problem.
Exactly. An App Engine application experiences a sharp traffic spike. It handles it, the load returns to normal. But for the next 10 or 20 minutes, users are still experiencing high latency. Why?
The symptoms are the key. Latency persists after the spike ends. This means the system scaled up, but the new instances were either slow to initialize or they were immediately shut down after the traffic dropped.
So the next legitimate requests are suffering from a cold start.
Right. App Engine tries to be aggressive with cost optimization by spinning down idle resources immediately. But that means when a new request arrives, it might hit an instance that is just, initializing the JVM, loading frameworks connecting to the database.
The cold start penalty.
The cold start penalty.
Yeah.
The solution is a direct trade-off between your cost and your latency SLO. The fix is to modify the App Engine configuration to ensure a minimum number of additional idle instances are maintained.
So you're pre-warming the capacity. You are intentionally paying for resources that are currently doing nothing.
You are. By setting a minimum number of idle instances, you guarantee that the application layer is warm, initialized, and ready to handle subsequent load immediately.
So when the next request arrives, it hits a waiting process instantly.
And that eliminates the latency associated with resource initialization. For services with strict latency requirements, this proactive cost investment is absolutely essential.
Okay, we've mastered scaling elasticity. Now we have to shift to scaling safety.
This is critical.
It doesn't matter how perfect your auto-scaling configuration is if the infrastructure layer just refuses to provision resources, or if your deployment process introduces a catastrophic bug. We need safety nets.
We have to dismantle the myth that the cloud is infinite. It's not. Cloud resources are constrained by limits designed for your protection, and they're known as quotas.
Let's use that analogy again because it just works so well. Cloud quotas are like a credit card limit.
That's a great way to put it.
They prevent you from accidentally launching a million VMs and bankrupting your company, but they also prevent you from breaking the bank for the cloud provider.
Right. By consuming more of a specific scarce resource than they have reserved for you in that particular region. It's governance, cost control, and capacity management all rolled into one.
And for intermediate engineers dealing with large deployments, quotas move from being just some administrative nuisance to a critical architectural constraint.
They absolutely do.
So consider this high-stakes deployment scenario from the sources. We're deploying a new critical service that scales using a MIG. It has to operate over multiple regions for disaster recovery.
And requires a demanding resource, maybe an expensive high CPU machine type, or even specialized hardware like GPUs.
What is the absolute non-negotiable first step for capacity planning here?
Before you check out the code, before you write any configuration, even before you get the budget signed off, you must validate that your resource requirements are within the available project quota limits of each region.
The very first step. Why? Can't we just assume the default quota is enough?
You absolutely cannot. Quotas are often set per region, and they can vary dramatically depending on the resource type, the region's maturity, and even your account's history.
So give us an example.
Let's say you attempt to deploy a multi-region MIG that needs 50 N2 Haishipu 96 VMs in Region A and another 50 in Region B.
Okay.
But Region B's default quota for that project is only 20 cores total. The deployment will just silently fail in Region B.
And the worst part is the failure mode isn't a clear error message, is it?
No, it's a silent inability to provision resources. The MIG will perpetually show 30 instances as pending, just waiting for capacity that doesn't exist. You'll spend hours debugging deployment logs thinking your YAML is wrong when the capacity was never there to begin with.
This is that distinction between a beginner and an expert. The expert views capacity planning as risk mitigation.
Exactly. If you require specialized resources, a high number of SSDs, specific GPUs, you need to submit a quota increase request weeks or even months in advance.
Because those requests often require human review and physical capacity validation by the cloud provider.
Right. Capacity planning is fundamentally about verifying your quotas and requesting increases well ahead of your deployment window. If you skip this, your multi-region scalability is just an illusion.
Once we've secured the capacity, we shift focus to securing the deployment itself. We want to get new features to production quickly, but if they contain a catastrophic bug, we need instant mitigation.
And traffic splitting is the answer.
Let's start with an intermediate strategy using Cloud Run, which is a popular choice for stateless microservices.
We have a microservice that's used internally by many applications, and we're deploying a new release. We need to test it rigorously without impacting any live traffic.
So the default canary approach is immediate percentage splitting. You deploy the new version and send 1% of live user traffic to it.
And if it fails, you roll back quickly.
But even 1% failure on a critical system is an incident. We want zero impact.
The sources outline a safer, zero-impact approach for this initial validation. The recommended action is to deploy the new version of the service to the staging environment with a unique new release tag, without serving any traffic.
Okay, so you deploy the revision, but you allocate 0% of the default traffic to it. So how do you test it?
Because every revision deployed to Cloud Run receives a unique, dedicated URL based on its tag. Something like new release my-service.region.run.app.
Ah, so it has its own private URL.
Yes, and this URL completely bypasses the main public routing layer, which is still pointed 100% at the stable revision.
So internal teams, QA, your CI/CD pipelines can all hit that isolated private URL with simulated traffic.
And perform full integration and load tests against the exact production infrastructure and configuration.
It effectively lets you use your production environment as a private staging environment. You guarantee the code you're testing is exactly what users will get, but without exposing that live public endpoint to any risk.
It completely eliminates user impact during that initial validation phase.
Okay, now let's graduate to the expert level. Simple percentage splits aren't enough anymore. We're in a complex GKenthos environment.
And we have strict requirements. We need to direct traffic based on specific user attributes, like their device type. And we need fine-grained, arbitrary percentage splitting across multiple revisions for continuous testing.
The moment the requirements mention routing based on an application attribute like device or user type, we know we've left the domain of standard Layer 4 load balancers.
We need Layer 7 intelligence.
So what's the solution?
The solution requires deploying the Canary release to Google Kubernetes Engine with Anthos Service Mesh. The mechanism is then to direct a specific portion of user traffic, say 10%, to a new version based on the user agent header configured within the Istio virtual service.
Okay, let's pull back the curtain on the technical components for this. Anthos Service Mesh is built on Istio. What are the key configuration objects that make this happen?
The two core components are the virtual service and the destination rule. The destination rule defines the available versions of your microservice, the specific GKE deployment or service endpoints, and the virtual service is the routing table.
It's the brains of the operation.
It is. Within the virtual service definition, you can configure a rule that says something like, if the HTTP request header user agent contains the substring Android, then route 100% of that traffic to revision B.
Wow.
And if the header doesn't match, then route 90% of the remaining traffic to revision A and 10% to revision B.
That is true policy-based routing. This level of granularity is essential for progressive delivery. You can roll out features to specific internal groups, specific geographic regions, or specific device types.
And you minimize the blast radius of any potential failure down to an extremely small, targeted user segment. It's just far superior to random IP-based or simple revision-based splitting.
So we've discussed when to scale and how to deploy safely, but both of these disciplines rely entirely on our ability to see and understand the system.
Absolutely. Scaling and safety are impossible without robust observability. We have to know why we're scaling and how we know the system is healthy.
The sources were implicitly using observability data all through the scaling sections, like when we said VMs are running at peak network throughput.
Right.
So it's vital for intermediate engineers to clearly distinguish between the two primary pillars, monitoring and logging.
They serve profoundly different purposes in an incident lifecycle. Monitoring is about real-time system health and performance. It uses metrics, numerical, time series data to inform immediate automated decisions.
It's like the car's speedometer and fuel gauge.
That's a great analogy. In our scaling scenarios, monitoring provided the data points that automated our decisions. CPU utilization and queue depth told the HPA when to add pods. Network throughput saturation told us when to scale vertically.
So monitoring answers the question, how is the system performing right now, and what immediate action should be taken?
Yes, it focuses on trends and aggregates. A drop in your availability SLI, a spike in latency, that's all monitoring data.
Conversely, logging is the historical forensic record. It captures discrete, structured text events from the application and the underlying systems.
It's not for real-time scaling. It's for post-incident analysis. It's the black box flight recorder.
So logging answers the question, what happened?
Exactly. You use logs for debugging. If a microservice failed after a deployment, you check the logs to see the stack trace. If a MIG instance crashed, the logs confirm the exact failure and verify that the automated recovery worked.
Both are critical, but one drives automation, that's monitoring, and the other drives diagnosis, that's logging.
Well said.
Okay, we've built the scalable, resilient, and safe architecture. The final challenge is continuous optimization. We cannot rely on intuition or tribal knowledge when we select resources.
We have to use data to ensure we're not overpaying for idle capacity.
And right-sizing is probably the most continuous process in cloud management.
It's the core discipline of matching your compute resources precisely to your actual historical workload needs. If you guess, you almost always guess too high, and that leads to chronic waste.
The challenge for most organizations, though, is just inertia. They have a global application running on hundreds of compute engine instances. Manually reviewing months of monitoring data for every single one is impossible.
It's time-consuming and it doesn't scale. We need a tool that uses historical metrics to select the optimal machine type with minimum human effort.
And the standard, lowest friction, and Google-recommended practice is to leverage automation.
Use the Recommender API and apply the suggested recommendations.
This sounds powerful, but how does the Recommender API actually work? Why is it better than just looking at a CPU graph?
The Recommender API goes way beyond simple snapshot CPU checks. It analyzes historical usage patterns, usually over the last 60 days, across CPU, memory, network I/O, and disk activity.
So it's looking at the whole picture.
The whole picture. And then it uses machine learning models to identify resource characteristics that would have provided similar performance at a lower cost, or, on the flip side, systems that are under-provisioned.
So if I was running a 4-core machine at 15% utilization for 2 months straight, the recommender would confidently suggest I move to a 2-core machine.
And say 50% on that instance's cost, because the historical data shows your peak utilization never even exceeded 30%. It completely automates that vertical scaling decision for you.
And it does more than just downsizing.
Oh yeah, it generates several recommendation types. Right-sizing recommendations, idle resource recommendations for flagging VMs that should just be deleted, and sometimes even migration recommendations.
Like suggesting moving from one machine family to a more efficient generation, like N1 to N2.
Exactly. It just takes the guesswork out of optimization. It makes continuous resource tuning a mechanical, data-driven process.
Our final optimization technique is about specialized compute for specialized loads. Preemptible VMs.
Or spot VMs, as they're known in other environments. These are the ultimate high-risk, high-reward resources. They offer massive cost savings, often 60% to 90% off the standard price.
But there's a big catch.
A huge one. The caveat is severe. Preemptible VMs can be terminated or preempted by the cloud provider at any moment, usually with only 30 seconds of warning.
So the primary skill here is identifying which applications can actually survive this arbitrary termination.
Right. You absolutely cannot put anything that maintains critical, unique state on a PVM. The application must be inherently fault-tolerant and distributed. The sources provide two canonical examples that really illustrate the patterns you need.
Let's start with the database example.
Yeah.
A distributed, eventually consistent NoSQL database cluster with sufficient quorum. Why is that suitable for PVMs?
Because of the quorum principle. Quorum means that data is replicated across multiple nodes, and a majority of them must agree on the state.
Okay.
So if one node running on a PVM is suddenly terminated, the cluster's redundancy ensures the database automatically fails over to the other healthy nodes.
Yeah.
There's no service interruption and no data loss, because the data existed on multiple nodes simultaneously.
The PVM node's death is just treated as a routine node failure, which the database architecture is already designed to handle gracefully.
Exactly. The application is resilient enough to absorb the inherent unreliability of the compute layer.
What about the other example? The GPU-accelerated video rendering platform that retrieves and stores videos in a storage bucket.
This illustrates the principle of idempotency jobs that can be safely repeated without changing the outcome. Rendering a large video is broken into many smaller, discrete segments.
So if a PVM rendering segment 42 is preempted,
The job for that segment fails, but the failure is managed. Because the input files are durable, they're stored safely in a cloud storage bucket. The failed job segment can simply be placed back in the queue and restarted on a new PVM instance later.
so the key is that the work unit is small, the inputs are durable, and the process is restartable.
Precisely. And conversely, the unsuitable use cases really solidify this understanding. A public-facing website cannot tolerate a sudden instance termination.
And a single, non-redundant in-memory caching system would suffer catastrophic data loss.
Right. If your architecture isn't built to assume that the underlying VM will just vanish immediately, you cannot and should not use preemptible VMs, no matter how great the cost savings look.
We covered a vast amount of territory today. We went from the fundamentals of scaling all the way to complex resilience planning and optimization strategies.
We did.
This deep dive should really arm any intermediate DevOps engineer with the knowledge to build truly elastic and robust systems.
I think so. To recap the major insights, first, true GKE elasticity requires that combined wisdom of the HPA scaling the application demand, ideally using custom metrics like queue depth and the cluster autoscaler scaling the infrastructure supply.
All tuned with careful stabilization delays.
Exactly.
Second, those network performance bottlenecks. They can often only be resolved by vertical scaling, a bigger, more expensive CPU, because network throughput is directly tied to the machine tier.
A critical, non-intuitive right-sizing lesson.
And third, scaling safety starts with capacity planning. You have to treat quotas not as suggestions, but as hard ceilings on your ability to scale.
Which means mandatory quota validation across every single region, especially for high-demand resources.
And deploying safely means using tagged revisions in Cloud Run for guaranteed zero-traffic testing and leveraging powerful L7 routers like Anthos Service Mesh for that policy-based header-driven canary routing.
That's a great summary.
We've covered the mechanics of elastic infrastructure, but true mastery really comes when you stop treating your resources, your compute engine instances, your GKE nodes, and even your quotas as fixed limits.
They're not static purchases. They are variables in an ongoing optimization equation, constantly being refined by data from tools like the Recommender API.
So our final thought for you to mull over. You now know how to build a system that can handle massive traffic spikes. But what percentage of your current cloud bill is dedicated to resources that are running under 20% utilization because they were sized based on intuition 2 years ago?
What existing monolith or chronically over-provisioned service in your environment could benefit most from a right-sizing recommendation today, turning that unused capacity into immediate, measurable cost savings?
Go forth, check your recommender dashboard, and optimize those resources. We'll catch you next time for the next deep dive.